Hello everyone, and welcome back to our series on searching and sorting algorithms part 4. In today's video, we will be breaking down selection sort. Let's dive in and see how this sorting algorithm works. What is selection sort? Selection sort is a simple comparison-based sorting algorithm. The basic idea is to divide the array into two parts, a sorted part and unsorted part. We repeatedly find the minimum element from the unsorted part and place it at the beginning of the sorted part, moving one element at a time. Once the smallest element is placed in its correct position, the process is repeated for the remaining unsorted elements until the entire array is sorted. When comparing to other sorting algorithms, selection sort may be very inefficient when it comes to time complexity, with a hefty time complexity of O of n squared. Okay, now let's start by breaking down the code for selection sort step by step. First, we initialize two variables, the minimum and minimum index. So minimum is going to keep track of the smallest element, and minimum index is going to keep track of the index of the smallest element. Next, we have the outer for loop. And the outer for loop will iterate through each element of the array. For each iteration or pass, we assume that the first element in the unsorted portion is the minimum, and we will assign its index to minimum index. Now let's move on to the another point, where we could see an inner for loop. And this loop will check every element in the unsorted portion of the array to find the smallest element. It starts with the next element after I, which is the index, and it will compare each value with the current minimum. If the current element in the unsorted portion is less than our minimum, we will update the minimum element to the element that is less than our current minimum. And we will also have to update the index of our minimum. Okay, now let's move on to the next step. After finding the smallest element in the unsorted portion, we will check if we need to perform a swap. If our first unsorted element is greater than our smallest element, we will have to perform a swap between these two variables. After a successful swap, we will have the smallest element at its correct position. Now let's look at the visualization example. In this example, we can see an array which is not sorted. It will be sorted after we have executed our selection sort algorithm upon this array. Firstly, we can see the index I pointing to 0, meaning that the for loop is starting from the start of our array to the end. Keep in mind that the index I is used in our outer loop, and index j will be used to index in our inner loop. And index j will always be the index just after the index I. First of all, we set our minimum as 12, and the index of our minimum is 0. We will use the inner loop to search for the smallest element in the list, linearly starting from the index j till the end of the array. Okay, now let's see how we can use the index j and the inner loop to find the smallest element of our array. First, we got number 21 as index j. When we compare it to our minimum, we can definitely say that we won't be needing to update our minimum. After moving on to the next index, we can see that j points to 15, and 15 is still greater than 12, so we don't have to update our minimum yet. Moving on, we can see that j is now pointing to 32. When we compare it to our current minimum, we can say that we won't be needing to update our minimum variable. Now, when j points to 10, the comparison shows that 10 is less than 12. Therefore, we will need to update our minimum variable to 10. Now we have our updated values. Minimum is now 10 and the minimum index is 4. Lastly, we will visit the last index, which is 5, and j is now pointing to 16. And again, when we compare 16 to our current minimum, which is now 10, we can say that we won't be needing to update the minimum variable. Here is the result of our comparison. For now, I will be pointing at 12. In other words, I will be the index 0, and our minimum variable and the minimum index will point to the index 4 and the value 10. After comparing the current and sorted to our minimum variable, the following condition to swap turns out to be true. Therefore, a swap between these two indexes or these two elements will take place in our array. Here's the result after swapping. Now, after the incrementation of I, we can see that I is now pointing to 21. Now, we will assign minimum to 21 and also the minimum index to the index of 21. After that, we will use the inner loop and the index j to iterate until the end of the array to find the smallest element. And this process will repeat itself until the whole array is completely sorted. On the surface, selection sort may seem such an easy and simple algorithm to implement. However, selection sort isn't the most efficient. Among the sorting algorithms, it has a time complexity of O of n squared. This is because every element in the array is being compared with all the remaining elements, which takes time proportional to the square of the array size. Here is a picture depicting the outer loop, which runs n times throughout the array, and the inner loop, which can run in a certain sequence. But if you are wondering how we determine O of n squared or other complexities, stay tuned. In future videos, I will dive deeper into big O notation and break down how we calculate these complexities step by step. I will show you exactly how algorithms like selection sort end up with O of n squared and why it matters. Now let's talk about the space complexity of selection sort. While its time complexity may not be ideal for large datasets, one of its advantages is its O of 1 space complexity. Space complexity refers to the amount of additional memory the algorithm needs to run. With selection sort, we don't need extra arrays or dynamic memory structures, just a few variables for the indices and a temporary variable to swap elements. Here are the variables used. First, it will be the array, which will be the array to be sorted. Next, we will use the variable minimum, which keeps or which stores the value of our current minimum. Next would be the minimum index, which also stores the index of our minimum. And lastly is the temporary variable, which will be used in the swapping of two variables. So as a result, this makes selection sort a good choice when memory is limited, even if the time complexity isn't the best for larger datasets. Okay, now let's write the code for our selection sort. Here would be the main method, which will be named sort. It will expect a parameter, which will be an array of integers. We will declare the minimum variable and the minimum index. Here will be the outer for loop. The loop will iterate until the end of our input array. We will assign values to our minimum variable and minimum index. After that, we will create another for loop, which will serve as an inner for loop, and it uses the variable j as its index. And keep in mind that the index j always starts just after the index I, and the inner loop also runs until the end of the array. Okay, here in the inner loop, we will have to create a condition check to find if there are smaller elements than our current minimum. If there is, we will have to update our minimum variable and its index. So if minimum is somehow greater than our element that we are currently checking, we will update the variable minimum to the smaller element, and we'll also have to do the same thing to our index. Okay, here this portion of code will search for the smallest element in the array. I mean the smallest element in the unsorted portion of the array. After that, we'll have to add the last condition check, checking if the unsorted part or the first unsorted element of the array is greater than our current minimum. If it is, we will have to perform a swap. So we will need the help of a temporary variable, and I will assign the value of the first unsorted element to temporary variable. Next, we will assign the smallest element to the position of our current unsorted element, which is at index I. So the element at our minimum index will go to the index of I. And lastly, we will assign the value of our first unsorted element, which is now stored in temporary variable, to the index of our minimum variable. So we swap these. After the swapping of these variables, we will have sorted position in our array, and after the repetition of these processes, we will have a sorted array. Now let's check if our solution is correct or not. So we will need the help of a test array. Here's a test array, just a random number or random numbers which are in unsorted order. Okay, that should be enough. Now let's perform the sorting algorithm on the test array, and we will print it out onto the console. Now let's run the code to see if it works. Okay, now let's check our answers. As you can see, our current implementation of selection sort seems to work well. Now let's sum up our today's video. While selection sort is easy to implement and has a small memory footprint, it is not the most efficient algorithm for larger datasets due to its very high time complexity. In the next part of the series, we will explore more efficient sorting algorithms and how they compare. Thanks for watching, and don't forget to subscribe for more content on algorithms.